Okay. Hello, everybody. Today lecture revolves around a test function, well-known test function called holder table. Holder table. This function is characterized by having 4 global minimum values which are equal and the same. And it has also a number of local minimum values. The value of the function in the global minimum value is equal about minus 19.2, as you see here. And because it is very similar to a table or a chair, it has 4 legs. Although it has the same global minimum value, but it has, of course, different coordinates for each leg of the table. And these coordinates also are standard and shown for you here. Minus 9.66, minus 8.05, or for example, the sign changes 9.66 and minus 8.05 and so on. So we have this situation here. We shall work on this function in this lecture by plotting the function in 3-dimensional space, then by plotting the contour of this function. We shall also plot the cost function as a value of iteration, dependent on iterations. Also, we shall animate the function in a 2-dimensional space and in 3-dimensional space. This is the first part of the lecture and will be done by using Python and Pyswarms library. In the second half of the lecture, we shall carry out similar activities by using LabVIEW. So let us begin. First, we need to plot this function in a 3-dimensional space, as you see here. This is the shape of this function. As you see, it has 4 legs and a number of local minimum values. And the surface itself resembles an egg tray, as you see here. In order to plot this function, this function is a 2-variable function. So we need to use the mesh grid of NumPy mesh grid. Before doing that, we need to define what are the modules, libraries, functions which are required to be imported. As you see here, we import from NumPy the range function, the exponential function, square root function, cosine, sine, Niberian number E, pi, the absolute value, and mesh grid. All these functions exist at NumPy. It deserves to say that maybe it is not necessary to import them in advance as I did here. Maybe it is sufficient to import NumPy itself as NP, and from NP you call any of these functions directly. You import NumPy as NP, and then you call the square root or the cosine or the pi or a range from NP library, from NumPy library. It depends on your taste. Because we are going to draw, so we need to import matplotlib as PLT. And because we need to plot in a 3-dimensional axis, so from multiple toolkits, we call also the mplot3d module here and import from it axis 3D. So these are the required methods and functions and libraries which we will work with. The expression of the function itself is shown here. Absolute of sine x multiplied by cosine y multiplied by the exponent of the absolute value of 1 minus square root of x squared plus y squared divided by pi. As you see, it is comparatively complex expression. We define this function as a function of two variables, x and y, as you see here, x and y, and we call it objective. So define or def objective of xy, return minus the expression of the holder table function. We need to define the range of x coordinate and y coordinates. First, we define the range minimum value and maximum values as -10 and +10. And then the x-axis is the range of the x-axis is defined by a range with r minimum, r the minimum value, r maximum is the maximum value, and the delta values equal to 0.1. Important to see that the range of the x-axis and the y-axis have the same number of elements. So now we have an array of values which represents the x-axis and an array of values which represent the y-axis. Note here that directly we used a range because it is already defined. If we imported NumPy as NP, we can here write NP dot a range. We call a range from NP instead of using a range directly. It depends how you prefer to do it. As we want to draw or to plot in a 3-dimensional space, so we need to convert the 1-dimensional arrays of x and y to a 2-dimensional arrays by using the mesh grid function. Also, this is a NumPy function. So mesh grid we pass here the x-axis array, which is one-dimensional array, and the y-axis, which is one-dimensional array. And as a result of that, we get x, y, new two-dimensional arrays. And now we pass these two-dimensional arrays to the objective function which we have, to our function, which is the table, the holder table. So objective of xy gives a variable, we call it result. As you know, in order to plot, we need to create a figure object. So from pyplot, we call figure function and assign it to a variable called fig. The same thing we do here in order to create a 3D axis on this figure. We call add subplot from the figure and pass the k argument projection equal 3D. By this, we are creating a three-dimensional axis on our figure. And now we need to plot. So from the axis we call plot surface, this is our function. Now we pass to this function x and y, and the z value or the results, which is calculated as the objective function with the new coordinates. For coloring, we call color map jet. Now everything is ready. We can save the created plot by using save figure function. So from PLT, we call save figure function and pass here the URL of this function. I call it holder table. Now it is saved, and PLT shows so as to see our figure. When we run this program, we shall have this figure as you see here. If I run it, yes, it appears, it is as you see here. Note that the x-axis and the y-axis are really between -10 and 10, -10 and 10. And this is the result which we have, or the z value of the function. So we have created the holder table function, and now it is also interesting to show you how we can plot the contour plot of this function. It is really not that difficult also. So as usual, we have to import the necessary libraries and modules and functions. And if there is necessity to create some data, we create. Of course, we are going to plot, so we need to create an axis values and for x and y. So for x, here we imported, as you see, numpy as np. So x is the variable which is defined by numpy dot arrange. As you see here, I didn't use arrange directly because I didn't import the arrange from numpy. I called it now from np. And I pass to this function the limits, the minimum value between -10 and 0, with an increment delta value 0.1, and the same thing I do for y. They are of the same length and size. Also, we use the mesh grid function to create a new two-dimensional arrays x and y. And now we pass these two-dimensional variables x and y in our function minus absolute so on, so on, so on. Now the variables here are those which are two-dimensional x and y, and we achieve by that z, or the result. In order to plot the contour, maybe it is necessary also to define the levels of the contours separately by using NumPy a range and defining the number, as you see, by between -2 and 2, and with a delta value .2. These levels determine the number and the positions of the contour lines. Also, it is useful always to establish or create a color bar for these values. Now, after defining the levels, we can pass the values or this array of the levels to the contour function. So from PLT, we call contour, and pass there the values, the initial values x and y, and the result z. And we also pass the levels, which is equal to levels. Yeah. Now the contour is established. We also can create a color bar to the contour. And after that, we save this contour in a file. We call it contour also. And here is what we have got. This is the color bar, the number between -2 and 2. Every interval has different color values, and they are divided, as you see here, and correspond to the colors of the contour lines which exist in the contour itself. So if we run it also, now we shall have this value, this figure as shown in front of you, between -10 to 0 and from 0 to 10. I selected these values specifically, especially because these values are necessary to allocate there the minimum value, which we will calculate by using the optimization Pyswarms. So what we have learned up to now, we have now introduced you to the function. We know what is this function. We have plotted the function in a three-dimensional space, and we have created a contour plot for this specific function. Now, what we are going to do is to find the minimum value of this function and the coordinates where the minimum value occurs. We shall use the Pyswarms library for that. And as a result of that, we can make use of the plot cost function. We shall plot it, and we can plot contour also of this function. So as usual, we begin our work with importing the necessary libraries. Here we are interested with Pyswarms. We import Pyswarms as PS. Pyswarms exist in Anaconda. I have downloaded it from Anaconda. Yes. And now we have, I want to tell you that Pyswarms also includes a file or a directory where there is a number of the standard test functions exist, and one of them is the holder table. So from Pyswarms utils, this is the utility library or module. We call the functions. From the functions, we select single objective function. We are going to minimize only one single objective function and import from there the holder table. So this function now, our holder table function, is defined and it is imported from the Pyswarms. Because we are going, of course, to make animations and to plot, we shall need matplotlib, so it is imported here. In order to plot the cost or the cost history and the contour, also from Pyswarms utils, plotters, we import plot cost history, plot contour. If we need to plot in three-dimensional space, we can also import plot surface. We shall do that later on. We are going to animate the motion of the particles, the trajectories of the trajectory of each particle. So we need to use a specific function for animation in matplotlib, which is called func animation. Note the capital letter F and A here. Also, in order to display the plots on the notebook, we can use the HTML function. I have imported it here, or the image function also I have imported it here. I shall show you how we can do it later. I am sorry. In order to establish in the figure a mesh, we need to use a mesher. This is an object of Pyswarm. And also, in order to, if necessary, to customize the limits of the x-axis and y-axis of the plot, we use the designer. So they are imported here. Of course, they are imported from the formatters. So after importing all the required material, we can begin writing our program. At first, we define our function and assign it to a variable. We call it objective function. So our objective function, it is indeed the holder table. Number of dimensions 2, x and y. This is known. The bounds of this function between -10 and 10, I take it -10 to 0. and from 0 to 10. These are the bounds which we will work on. Now we have to assign the static values of the coefficients C1, C2, and W. Reminding you with this function, with these constants, C1 and C2 are usually called the acceleration constants or the learning constants. They are constants, but they are adjustable. You can select their values depending on your needs, of course. And the range of selection here is not that large. It is between 0.1 to 1. This is about C1 and C2. Generally speaking, C1 and C2, these are coefficients which define the behavior of the particles themselves, and their values affect the performance of the Pyswarm. C1 indeed shows to which degree the particle is confident of its intelligence, and C2 is a value which represents the degree of confidence of the particle with the neighboring or the swarm itself. The philosophy of Pyswarms depends on the mutual cooperation, interaction between the experience of the individual particle and the whole folk. So C1 and C2 must be always together and must be close to each other, because if we consider C1 is too high in the higher upper value possible, this means that this particle depends mostly on its experience, and it will lose a lot of time seeking for the best position, and it doesn't make use of the experience made by the neighbors. And if we do the other thing, and only we can depend on C2, making it high and ignoring C1, so also we are missing the experience of each individual here. Usually, as I told you, C1 and C2 between 0.1 up to 0.9, and they are usually taken close to each other between 0.2, 0.3, 0.4, 0.5, like this. W is taken from weight. This represents the inertia of the swarm. And as you see, I have selected it equal to 0.5. This value may be higher, maybe 0.6, 0.7, 0.8. The higher the value, the more inertial the motion of the swarm, and the best the convergence, yes, character here. It doesn't take a long time for convergence. Sometimes when we use a ring topology of the Pyswarms, it is required to add to these constants another constants. One of them is called K and the other is P. And K generally represents the number of the neighbor or neighboring particles which is suggested. And P, really, it is an integer which is equal to 1 or to 2. You have to select between 1 and 2. So as you see, knowing what is C1 and C2 and W is not that difficult. And I have maybe more than one time tried to explain it to you. We now define the number of particles which we are going to work, the number of particles also, and the number of the iterations which are going to take place also affect the performance of the swarm. If we select a large number of particles and a large number of iterations, we are going to occupy a large memory area, and the process will take long time to converge. Generally, as an advice, we use the number of particles between 20 to 30, and this will be sufficient. But the number of iterations, I have taken it here about 500. Really, this is decided by you when testing the program, because sometimes you may feel or notice that the cost function comes to a minimum through 50 iterations, and you may not need 500 iterations. So to make the process quicker, you can adjust the number of iterations to a lower value, and sometimes you find that there is still an error, not small error, a large error comparatively, and you need more iterations to go on to refine the process and to come to the minimum value. So the iterations value also, as a general, you do not need to have it very high, but it depends on the accuracy level you are targeting. So, as you see here, we call the optimizer. From the optimizer, we call optimize. Before we say looking at that here, from the Pyswarms, we call the single objective function. We are going to make minimization by using a global best particle swarm optimization. And for that, we need to pass the required data to this function, the number of particles. You can write directly here the number. The dimensions, you can also write directly the number. If it is assigned previously, you can, for generality, you can write in textual form or as a number, the bounds which are already defined by you, and the options which are already defined by you. So the options and the bounds and the dimensions of the variable of the function, number of particles are all known to us. And now we can call from the optimizer the optimize function and pass there the objective function, which is the holder table. It requires the number of iterations, so I added iterations equal to 500. Now I get as the output two values. As a result of optimization here, I get two values, the best value, which means the minimum cost. This is the optimal minimum cost value, and I get the coordinates or the position where this best value occurs. In other words, I get the optimal values of the function itself and the optimal values of the location. And now I need, of course, to plot how the cost changes or varies by iterations. The optimizers include a position history and include a cost history. I can find the position history by calling from the optimizer history, and I find the cost history by calling it from the optimizer also. So the optimizer dot position history, it gives me the position history, all the values of the positions of the particles, the position of each particle at each iteration. This is the history. The position for each particle for each iteration is given here. And also I get the same for the cost. So in order to plot the cost, I need the cost history. So plot cost history, this function, I pass to it the cost history itself, and now it is plotted. PLT show is to show you the results. What I am expecting here, I expect to see the minimum value, how it changes by iterations. If you look at it, this is the cost function, which represents the minimum value and how it changes by iterations. As you see here, really, convergence takes place in this region. About 100 iterations are required and not 500 as I suggested. So you can adjust the work done before and write instead of 500, 200 or 150, and it will work fine. Also look here, the minimum value here is minus 19.2. This is exactly what we expected when we learned the data of this function. When I gave you an idea about this function here, the minimum value is minus 19.2008. So exactly it is computed, the minimum value, this minimum value for this leg, and it is the same for this leg and the same for this leg and for all the legs. So the work is very accurate. This is minus 19.2, and it is a little bit lower because .2.8 also are added. Now we need to show the position where the minimum occurs. The measure here, which I noted before to you, is not used. I have cancelled its use, and I will work without a measure. So just to show you how. I kept the designer and I assigned the same values from minus 10 to 0 and from 0 to 10 at the upper side. And this is X and this is Y. So I kept this for the designer. And note that these values now are newly introduced to the designer. The default values of the designer are minus 1 and 1. So I have changed them according to the situation here. Now the designer is known. The position history is known because we have defined it by calling it from the optimizer here, optimizer dot position history. We have the position history here. So we know the position history. Yes. So from the plot, and the plot contour is also imported before. I have imported the plot contour. Here it is imported. So the plot contour syntax requires the position history, the positions so that it can be plotted, and the designer object so that to know the limits. And also here is a possibility to fix on the plot the coordinates of the point where you expect the minimum will occur. But we know the minimum will occur at a point 9.66 and minus 8. Here it is. 9.88 here. 9.66 and minus 8.5. So in advance, I know one of these coordinates, any one of them is a candidate to be a coordinate value of the minimum for any of the legs, of the 4 legs. We have 4 values for the 4 legs. So I suggested, so that to note how the particles move, I suggested to put on the figure, on the plot, to lay or to fix on the plot a point with coordinate 9.66 and minus 8. It is called a mark, assigned a mark. And now I have the plot and I can see it. Having the plot, I can save it. The variable here for this plot is called anim, from animation, on 2-dimensional space. Anim dot save. I pass here the URL of the file. I call it plot65 GIF. And the writer is ImageMagick. I have downloaded and installed ImageMagick on the computer to write the file, the image. The number of frames per second is suggested to be 10. In order to see the plot, to watch the plot on the notebook, I use HTML function. As you see here, I pass to this function the animation variable, anim, dot to JavaScript HTML function. This is a standard form. By doing that, I can also get the plot alone, and I can always run this plot without running the whole program. This is really very interesting because animation takes place, it takes time, and comparatively long time. And in order to save time, to show you or to show anybody, you can run this function alone without running the whole program, and you can see the results. So this is the cost function, as you see, as a function of iterations. And this is the minimum value is shown here. Here is the mark with red is the suggested point. And here is really the point, the exact point where the particles converge and find the minimum. So this is the location on the contour plot or plot contour. And note here that we do not have any mesh. it is clean. Only I have here this dot. Downwards, you see this is the mark which I suggested. This figure now is plotted by using the HTML, and I can run it directly, as you see from here. I can run it directly using a loop or for one time. Let us run it by using the loop, and you will see that all the particles are converging to that point, which means that the system is working very nice and without any problem. As you see, they all converge to this point. And the coordinates of this point, as you see, this is number 8, this is number 10. So it is about 10, it is 9.66. This is 9.66 here. And the abscess or the x value is about minus 8. It is the same here, minus 8.05. It is the same, minus 8. Also note that when we carry out this optimization by using the Pyswarms, we get from the system directly in a written form the minimum value, which is the optimum minimum value, minus 19.2, and the best position or the optimum position, which is 9.66 minus 8.05. So as you see, the function is working very nice. Pyswarms works efficiently. There is no problem. You do not need here to carry out any derivations of the variables, especially when you have two variables. You do not need that. Directly follow up the instructions and you will get the results. Here, now we shall do the same thing. Let me stop it here. We shall do the same as we did before, but by keeping the mesh object. So this is the contour plot of our function. This red crest here is the mark. And this dot, the black one, represents the conversion point where all the particles converge. And I hope, yes, I have done it here. And downwards, I have done it by using the HTML. If I run the HTML now, I see that all of them converge to the same point. Really, the program only includes an additional instruction here, which is the measure here. And of course, to this measure, you need to define which function you are going to work with. It is the holder table assigned to the func, which is the, and the limits which are used by the designer here, minus 10 to 0, and from 0 to 10. And the other information is the same. And we get the same answer and the same results. Also, remember, we have saved the result as a file. Here it is called plot68.gif. And here what it is called 65.gif, for example. Let us see how we can really also read the results from this file. So we can go to the computer, see users, del, and here we look at our plots, they begin with the letter P, so this is the P, plot 60. I have forgotten the number, 60 what? 65, I think it was 65. If I run it from here, yes, this is the case where we did not use the measure. The second one was given a name 68, I think. Yes. Yes, it is. So as you see, it is also existing here and you can run it directly. This is interesting and very useful for you. One also interesting thing I want to tell you here is, suppose you have this file in Python and you need to display it in LabVIEW. How we can do that? We go to LabVIEW, we open LabVIEW, okay, and now I am here. This is an untitled block diagram. What do I need? I have to go to the plot where it is here, drag it, press it and drag it to the block diagram and leave it there. Now I have here, if I enlarge it, I have it here in LabVIEW. And I can run it in LabVIEW. I can save it in LabVIEW. Save as, for example, untitled one now becomes, let me call it, for example, Sammy VI. Okay. We leave it now. We do not need LabVIEW anymore. If we go to LabVIEW files, here they are optimization with LabVIEW. Here is Sammy VI, as you see. Now I can run it from here. Here it is. It works, as you see. This is very interesting, okay? So, we have learned many things up to now, but let us continue our work. We have let me go and call my program newly, Jupyter Notebook Classic. I am very sorry. Okay, I am here. takes some seconds to work with. Now we are back to our example. So here our function. Now we have done all this work here. This work is done. This work is done. This one is done. And we are here. The last thing I want to show you today is how to animate the holder table function in a three-dimensional space. So as usual also, we need to import all the necessary modules, libraries, sublibraries, or functions. What is important here? Not to forget the func animation function to be imported from animation, because you are going to animate. And in order to animate, you need, of course, to find the cost history and the position history. So we use the Pyswarms. And from the Pyswarms, we call our function the holder table. We call from the plotters plot cost history. We establish 3-axis plot, and we import the measure and the designer. Okay. Now we define our function, the holder table, as an objective function, as we did before, the same range of x and y values, the same values I have kept for the options of the swarm. I am going to use the global best PSO also without any change at all up to now. All what I have done here, I have called the optimize function from the optimizer, passed there the objective function, which is the holder table, and the suggested number of iterations. Now this function is supposed to give me, to supply me with the optimal value of the cost and the optimal value of the position. This is normally which we did before. What is interesting here, because we are going to animate the trajectory of the particle, so we need to follow up the position. So the position history is important. So from the optimizer, we call the position history and assign it to a variable. We call it position history 1, for example. This is a new variable now for the position history. In order to work with the position history, as Pyswarms do, it is generated as a list and not as an array. So we need to convert position history 1 to an array. So np dot array, we pass here the position history 1, and we get a new variable with the name position history. But this position history now is an array. So we can find the shape of this array. Position history shape, it gives you 500 particles, sorry, 500 iterations. Each iteration has 20 particles. Each particle has two positions, X and Y. Remember, here is 500, and I remember here it is given 1000. So this must be corrected to 1000. Just for knowledge. It doesn't affect the work, but to be compatible with this value here. So now I know the shape of the generated array, and I can print all the positions of all particles for all iterations. Print position history. If you look at it, really it looks very long. No, here it is. This is the position history. This is X and Y. As you see, X and Y are given as lists, array of lists here. And this, of course, these dots represent that there are also many of these things here, 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 until you come to the end. The total of these lines must be equal to 1000, but they are not shown here. The program to save memory does not show them all. If you want, you can see them. But what is the most important here? The most important, look at the last value or the last values which you get. These values, X and Y represent the values at the end of iterations. This is the last iteration. This is the pre-last one, and so on. So they are very close to each other. 9.6659, it is the same practically here. And this is the Y and this is the X value. As you see, these values which are given when running the program. Remember, minus 8.05, 9.66. If you go up, here, you will see that this is the value of the cost function at the minimum value, and these are the values of the coordinates, minus 8.5, 0.05, 9.66. These values are the last two values of X and Y, which they are the last accurate, the most accurate values, where the iterations stopped. And this is the function at this coordinates, the value of the function. Here I didn't draw it. It seems I didn't draw it. I didn't try to draw it because I have drawn it before for you. Now, so we are here. We have the position history. We are going to work with the position history. The position history reflects what is going through iterations. And in order to carry out the animation, the function, which is func animation of matplot library, this is usually called from animation module, func animation. It requires to define in advance the figure where you are going to animate and the function which is going to be animated. So here, at first, I have to create a figure. I call from PLT figure function and assign it to a variable called fig. And on this fig, I create an axis here with 3 axes so that I can see animation in 3 axis plot. Then we can set the labels of X and Y and Z. We can also fix the or set the X limit and the Y limits. And they are already defined by us by, really they are not 5 and 12 here. This is because these values were taken from Rosenbrock and not because for this function. These values will become minus 10, 0, and 0 to 10. Okay, now this is the measure which requires to know for which function we are going to work, the holder table. I didn't include any new things here. And now we come to the most important in Pyswarms. In Pyswarms, we need to animate in a 3-dimensional space. And the Pyswarms themselves are 2-dimensional, X and Y. They are X and Y, as you see, I have shown you. In order to create the Z value, which represents the height, the third coordinate, Pyswarms gives you a facility to use a specific function there, which is mesh compute history 3D function. In order for this function to work, all what you need to pass there, the position history. Optimizer dot position history, you pass it to this function. You will get now a new array position history 3D, which has 3 values, X, Y, and Z. I didn't show it to you here. I can show you if I want to plot it where I am. Yeah, position history 3D. Ah, yes, it was done for you. Let me show a print here, position history 3D. Okay, I want to show you only for the first 0 index iteration for all the particles, for all the positions X, Y, and Z. Again, so I want to show you the position history in 3 dimensions for the first iteration with index 0, for all particles of this iteration, which are 20 or 30, and for all positions, which are 3. So if I take away the hash from here to enable to work with it now, and if I run the program here, run, the program is running. Yes. We have got the first one. Here is the array with the 3 values, X, Y, and Z. And this array is only for the first iteration. And because we have 20 or 30 particles, so we will have this information for all the particles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It seems they are 20. So it works. But if I go to the function here, you see this asterisk. This means that the program is still running. The program is still running. It doesn't finish working. Why? Because I am working on animation. The program is ready for animation. So what I have done here, I have only created the figure and the axis. I have used the measure, and I have converted the position history to a three-dimensional position history. And now I want to make animation. Animation is going on, as you see. It takes some time. Meanwhile, I want to tell you what I am doing. First of all, this function, which is func animation, requires two steps to be done. One of them is not that compulsory. You can do it differently, but here it is done as it is in matplotlib library. So we define the variable x, which represents the position history at the initial state for all the iterations, for all the particles, only for x. The position history for all particles, for all iterations, all particles for y. And now I have the third position history 3D for all iterations, all particles. 2 is the index of the third coordinate, which is z. This is x, this is y, this is z. So initial values for x, y, z for all the particles, is given. And now we can give a scatter plot or draw a scatter plot for this initial case. Ax scatter, x, y, z, color is blue, the marker is, as you see, O, and the labels is particles. It is given a name particles. So what we have done here, we have defined the initial position of x and y and z for each of the particles here in the program. Now we want to animate. We do not want to work with only one iteration. We need to work with a number of iterations, defined by I, which is the index, beginning from 0 and ending with 1000, which is the number of iterations. So we need to find x for all iterations, I, which is I now begins from 0 and ends with 1000 for all the particles for position x. We also define for all iterations, for all particles, the y value, and the same thing we do for z. And now we introduce the last function, offset 3D function, which enables to move from to update from one iteration to another iteration of x and y and z. By this, everything is ready for the func animation function. The figure is existing. We have made a figure. Func animate, this function is already created, which shows how updating takes place. The frames, the number of frames is equal to the number of the iterations, which is 1000 here. I can take this away and put 1000, it is the same. The interval between frames, 150 milliseconds. And I do not want any repetition of the work of the whole swarm. I have suggested to have a legend at the upper left corner of the figure, and I am saving this animation to a file called plot39gif. Now, when this figure finishes here, if it is finished, it is still going on. When it finishes, it will show me a three-dimensional figure with the particles converging to the point which is the optimal point as we have seen before. It seems to me to this point, 9.66 minus 8.5. It seems to me it will take maybe 1 or 2 minutes. Let us watch it together and see what is going there. The not good thing in animation, as I told you once, is that it takes time, a long time, comparatively, in order to make the most important, which is the optimization of the function and plotting the cost function. It takes maybe 2 to 5 seconds, not more. But the animation process takes time in minutes. About sometimes it took from me 5 to 10 minutes. It depends. Why? I told you it depends on the number of the. No, it is finished now. As you see, if I go downwards, I shall see something new here. What I found here is the 3-dimensional space. All the particles are converging to this point. What is the coordinates of this point? As you see here, this is -10, this is 8, and this is 9. This is 9. I'll show you. 9.66. This is Y. This is 8. This is 10. 9.66. It is here. Now, X is -8 approximately. This is not -8. Here is the point. And Z is equal -19. You remember, .2. This is -19.2. So this is the point in the space, in the 3-dimensional space, where convergence takes. Let me show you this also, because I didn't here use the HTML function. Let me try to show you from the figure. Plot 39, GIF. Let us go there. Plot, this is PC. Plot 39, GIF. If you go to plot 29, 39, it is. Now look how they are all converging to this point. Okay, I think the idea now is clear. What we have done today up to now, I have introduced to you the holder table function with its specifics. We have plotted this function in a 3-dimensional space. We have minimized this function and plotted the cost function and made sure that this function really has a minimum value -19.2. And after that, we animated the particles' motion in 2-dimensional space without a measure and with a measure. And at the end, we animated the trajectories of the particles in a 3-dimensional space, as you see here. And we are sure that all the particles are converging to the specified point here, where the minimum is -19, about 19, and the X value about -8, and the Y value is about 9. Really, I was intending to show you similar activities which must be done by using LabVIEW. But the lecture is very long, and I think it is preferable to keep it alone And I promise within a day or less, I will summarize to you how we can do the same activities with LabVIEW for the same function. The most important for the same function. Thank you very much. Wishing you the best. Goodbye.